Okay, well, let's get started. So as usual, don't forget the seating survey, section 4, ILC 118. Upcoming deadlines, we have homework due on Friday, 3 parts, and the small group activity is live now and is due on Tuesday of next week. Do we have any logistical stuff to talk about before we get into some content? We're good? Okay. Let's go. Several sort of muddiest points that we had right here, and I want to address a couple of them individually, but then a few of them I kind of want to address together in a sort of extended example that we can work through on kinetic mechanisms and such. So looking first at the ones that we can just sort of address individually, there was a question about the activation energy content video. A particular reaction was listed there, and the question was, how do we know it's exothermic? So let me share a screen and switch this so people here can see it. So this is the point in the content video where the reaction between O2 and a hydrogen atom was brought up. And the question was, how do we look at this reaction and know that it's exothermic? Does anyone have a suggestion about that? Yes? There's a release of energy. The products are at a lower energy state than the reactants, so therefore that extra energy had to be released. That's exactly correct. So you aren't supposed to necessarily look at O2 plus H by itself and know that it's exothermic, but looking at it with this diagram and seeing that the products are at a lower energy state than the reactants, that information should tell you that it's an exothermic reaction. Okay. Any clarifying questions on that idea? Okay. How do you tell if the frequency factor is going to be large or small? And so knowing that it has to do with orientations, but how can you tell when looking at the molecule? Just looking at the molecule probably isn't going to be enough for you, but you need to be told a little bit about how the reaction is going to happen. First, let's make sure we know what we're talking about when we say the frequency factor. So in the Arrhenius equation, we have a pre-exponential coefficient times e to the negative activation energy over RT. And so this is the formula that we use to model the temperature dependence of the rate of reaction. And the A that is in front here is known as the frequency factor or the Arrhenius factor. And the idea is that if a lot of mutual orientations work in a particular collision, this will be a large number. If only a very restricted set of mutual orientations will work, then this will be a small number. So it's kind of a correction to, this term right here determines what fraction of the collisions have enough energy to get over the activation barrier. This factor right here tells you which ones are pointed the right way to make it happen. So in order to evaluate this, you would have to be told something about what's the nature of the reaction that's happening. So for example, if the reaction were 2 iodine atoms coming together to form an I2 molecule, there's no orientation dependence here because the atoms are spherically symmetric. So the A factor here would be quite large. But if you had a reaction where there was maybe, let's say, carbon, something like this, and you have an iodine molecule, an iodine atom that is coming up and it has to hit the back of this carbon atom in order for it to react, then there are lots of places it could hit that's not in the right spot. And so you would have a very low Arrhenius factor or a very low frequency factor in this kind of case. That is not the kind of thing that you would be expected to just know. You would have to have some information either told to you about to make that happen, or maybe you are told that the product of this reaction looks like that. And if you're told that, then you would know that the iodine has to hit this carbon at some point. Hitting this carbon over here is not going to be able to cause the reaction because of simply where it ends up. So the idea is that you have to be able to look at what the reaction is and either be told or be able to figure out from what you're given what's the sort of target that's on the molecule that the collision has to happen at. Does that general idea make some sense? Okay. All right. I'm going to address these three together in an extended example in a minute. It's going to be kind of an exam style kind of question that I'm going to go through for looking at these three aspects. So let me clear up this last one first. In the small group activity, there was a question about the numbers that are under the reactions and what exactly that means. So let me call that up. Let's go here. Let me switch so everybody can see it. I'm actually remembering this time. Okay, so we have this figure here, and there are numbers which are times under each arrow. So the first one's 4.46 times 10 to the 9th years. The next one's 24.1 days. All of those are half-lives. The question that was asked on Piazza was, are they half-lives or are they the time it takes for this to decay 100% away? Let's think about that question for a second. If we have a first-order decay where our concentration equals our initial concentration e to the minus kT, that if it were something like when does it 100% decay away, then this would have to be 0, right? So it would be 0 equals something here. So that's going to go away. When is e to the something, what's the time we would have for this to be 0? The only way that would work is if t were infinity. E to the negative infinity approaches 0. So what this means is that in kinetics, no reaction is ever fully 100% complete, because the mathematics say that it never goes all the way to 0. So the answer to the specific question was that it's half-lives, but that brings up this other issue of how do you tell if when does a reaction go to completion, and the answer is really never. It can get close, but not really ever. Okay, the rest of the questions I want to do an extended example. And so the idea for this example is to look at a reaction 2NO plus O2 goes to 2NO2. And what we're going to do is we're going to compare two different possible mechanisms for this reaction. One of those mechanisms is, so I'll do one mechanism in green, one mechanism in blue. So one mechanism would be NO plus O2 goes to, call this K1, goes to NO3. We will say that this is a reversible step, so we'll have a K-1 associated with it. And then NO3 plus NO goes to 2NO2. We'll call that K2. So that's one possible mechanism. A second possible mechanism would be NO plus NO, which you could certainly just write as 2NO if you wanted to, goes to 2 into O2. I'll call this K3 and K-3. And then into O2 plus O2 goes to 2NO2. And so both of these have the same overall reaction, and they are both proposed mechanisms for how this top blue reaction happens. What we are told as well is that in this case, this is a fast equilibrium, and therefore this is the rate determining step. And we are told as well in this case to treat into O2 as a steady state intermediate. So in the context of getting a question like this, you would be told all of this information. You would not have to figure out what the rate determining step is. You would not have to determine whether you should use the steady state approximation or not. You would be told that kind of information. Okay. Do you have any questions on the setup of the problem here that we're trying to look at before I get into analyzing these mechanisms? Okay, so let's do the top one first. And what we want to do is figure out what rate law this predicts. So if this is the rate determining step, then we write the overall rate as the rate of this step. Can somebody tell me what I should write down for the rate of this step? Okay, so K2.
KNO squared.
K2, what was the other part? Oh, that was over the chat. Okay. So the way we do this is we take the rate constant for that step multiplied by the reactants for that step raised to the powers of their stoichiometric coefficients, which are 1 in this case. So NO3, NO. Now, if we look at our overall mechanism, if we look at our overall reaction, which is up top, we see that NO3 is not part of this reaction. It is something that is created by the first step. It is destroyed by the reverse of the first step, and it's destroyed by the last step. So the NO3 is a reaction intermediate. And so we need to get rid of that in this expression. So we are told that this is a fast equilibrium. What does an equilibrium mean in terms of the forward and the reverse rates?
They're equal.
They're equal, that's right. So we take the forward rate, which is K1 concentration of NO, concentration of O2, and set it equal to the reverse rate, which is K-1 concentration NO3. The thing we are trying to get rid of is the concentration of NO3. So let's solve this equation for that concentration. Okay. And now we can plug this in here. So we find our overall rate is going to be K1, K2 over K minus 1, concentration NO, one from here, so squared, concentration of O2. So this reaction mechanism predicts that the overall reaction, the rate law will be second order in NO and first order in O2. Are there any questions up to that point? Okay, let us now look at the second mechanism that we are comparing it to. Okay, so yeah, that should be visible there. Okay, so in this case, we are told to treat N2O2 as a steady state intermediate. So it is certainly an intermediate because it does not appear in the overall reaction we're looking at. For steady state, we need to have the rate of production of the intermediate equal the rate of consumption of, or destruction of the intermediate. We only have one step that produces it, which is this K3 step. Oh, I didn't mark a rate constant on this one. We'll call this K4. And so our rate of production is going to be K3 concentration NO squared. For the rate of destruction, we have two steps that remove it. So we have the K minus 3 step. So this is going to equal 2, no, excuse me. Okay, let me back up here for a second. So when this boy, I'm done, this isn't right. That should not be a 2 right there because we only have, that would not, the number of atoms wouldn't work. Okay. Now, our rate of destruction, we have the K minus 3 step, so K minus 3 concentration N2O2. We also can have it destroyed by this step, the K4 step, so plus K4 concentration of N2O2, concentration of O2. Now, we are treating the N2O2 as a steady state. So just as a reminder for that, I'm going to label that with a subscript SS for the steady state. And that tells us which quantity we want to be solving for. So I'm going to factor the N2O2 concentration, steady state concentration out on the right-hand side. So we have K minus 1 plus K4 concentration of oxygen times N2O2 steady state is our K3 NO squared. We can now divide through by this thing to get the N2O2 steady state by itself on the other side. So K3 NO squared over K minus 1 plus K4 O2 equals concentration N2O2 steady state.
I'm confused why we're using K sub 1 or K negative 1 for N2O2.
Confused about the -1 here?
Up one step.
Up here.
Yes.
Okay. So the K, oh, that should not be a K minus 1, that should be a K minus 3.
That makes more sense.
Yes, indeed it does. Thank you. Okay, so this should be a 3 there as well. Okay, Now, we need to figure out what we're plugging this into. So since this is the step that is producing the products, we're going to call this the overall rate. So our overall rate is going to be K4, concentration into O2, concentration of O2. And now we can plug this into here to find the predicted rate for the mechanism. So it's going to be K3, K4, NO squared O2 over K minus 3 plus K4 concentration O2. Okay. Now, another piece of information that you would be given as part of this problem would be that this step here is very slow compared to this step here, meaning that whenever the N2O2 is made, most of the time it goes right back to NO, but only occasionally goes this way. Okay. So if we are given that information, then that tells us something about the magnitude of this compared to this in the denominator. So the fast one is the one that is going to be big here because it's the rate. So the K minus 3 step is fast, and so this here becomes negligible. And we are left with K3, K4 over K minus 3, concentration of NO squared, concentration of O2. All right. So now there are a couple of things I want to point out. The first is if we look at our two mechanisms, we end up with, in both cases, second order in NO and first order in O2. So just from the reaction orders, we can't necessarily tell the difference between these two. But now suppose you are tasked with the job of designing an experiment that would allow you to distinguish between these two. Is there anything you can think of you could do that would help help distinguish them? And I'm going to give you a hint. It has something to do with this part right here where we said this bit was negligible. How fast the reaction occurs, like overall? A little bit, but what would you do experimentally to test that? Is there something we could do to make this term in the denominator that we said was negligible not be negligible anymore? How could we make this? We crossed it out because it was slow, because it very, very seldom happened. What could we do to make it happen more often? Possibly a catalyst, but I think there's an easier way right now, even without a catalyst. Notice that there's the concentration of O2 right here. This step, K minus 3, if we go back and look at what that is, doesn't depend on how much oxygen there is. But this step will speed up the more O2 that you have. So we could flood the system with O2. So take the pressure of the pressure of the oxygen gas that you have and just crank it up to 11, right? And you do that, and suddenly this term is the big one, and this one's the small one. And if that's the case, then we have K3, K4, NO squared O2. Make sure I'm still on screen, yep. Over this instead of that, K4, O2. K4s cancel, O2s cancel, and you now have K3, NO squared. So if you flood the system with O2, and then the reaction stops depending on how much O2 you have, then that would be support for this mechanism. So what you could do then is plot your rates as a function of concentration of O2. So you're plotting your overall, maybe initial rates or something, doing that. And it's going to start off linear because it's first order in O2. But then if this mechanism is right, it's going to level off and stop depending on O2. So that would be a way to distinguish these two mechanisms. Another thing I'd like to point out, let's suppose that we're still operating in this regime right here. And let's suppose as well that we know something about the activation energies of each of these rate coefficients here. So we'll say that our K3 has an activation energy of 79.5 kilojoules per mole. We have a K4, let's do the K minus 3 first. K minus 3 has an activation energy of 205 kilojoules per mole. And our K4 has an activation energy of 84 kilojoules per mole. So if we take this expression here, K3, K4 over K minus 3, minus 3. And if we plug in the Arrhenius equation for each of these, the pre-exponential for step 3, e to the minus EA3 over RT, A4 e to the minus EA4 over RT, all over, that should be a minus 3, A minus 3, E minus EA minus 3 over RT. We can combine some terms here so that our pre-exponential becomes A3, A4 over A minus 3. We can combine these terms just by using the properties of exponents to become minus EA3 plus EA4 minus EA negative 3 all over RT. And so this still looks like the Arrhenius equation with an activation energy that is this one plus this one minus this one, right? Now, if we do that, what kind of number do we get? So let's just, we can plug it into a calculator, but 80, 85, that makes it about 165 between these two, minus 205, we're going to get a negative activation energy. So if we have a negative activation energy, what does that say about the speed of the reaction as we increase the temperature? Will it go up or will it go down? It'll go down, that's exactly right. So what's happening here is that because the reverse step here has the biggest activation energy, which is working against the reaction, in terms of the temperature dependence of the reaction, that step is going to dominate. You heat it up, that step gets faster and faster. And so we end up with a negative overall activation energy and a reaction that gets slower as we heat it up. Okay, so this kind of analysis that we did right here had combined a lot of the concepts that we've been talking about here. And so this is the kind of question I would try to guide you through in an exam kind of context. So comparing different mechanisms, where in one case you have one set of assumptions, in another case you have another set of assumptions, but in every case you're told which assumptions to make. And then thinking about the results that you get to see, is there a way to tell the difference between them? And then what are some of the implications of it? And here, one of the implications of the activation energy is kind of an interesting implication. Okay. Does that make a little bit of sense? Okay. Any questions on anything in this example we went through? Yes?
Like in lab, we did something similar to this, where we found like, we made a diagram of melting boric acid and then find the freezing point of it.
Mm-hmm.
Would you ask us something similar to that and test of like giving us a graph and then comparing it to something else and seeing where they intersect or something similar to that?
So let me see if I understood the question correctly. So you're saying in lab you had a case where you were measuring the freezing point of something,
Yeah.
and you were what was it you were plotting?
Essentially like a cooling curve,
Okay, like a cooling curve.
like a reaction rate of it, and then we had an unknown, we compared the two to see how they interact with each other.
Okay, so you had an unknown, you were comparing them and seeing where they intersected. So I don't know, I'm having a hard time visualizing what the actual background of that experiment was. So I can't necessarily say I would ask you to do that or not. Certainly looking at experimental data or pseudo-experimental data and trying to analyze it compared to a model is absolutely something I could do. I am working right now, I've mentioned this a couple times in class already, but so you may have already heard this, but I'm working right now on putting together an Excel spreadsheet that you guys can use to generate simulated experimental data, which you can then copy and paste into your own spreadsheet to analyze for kinetics. And I'm going to, I can pretty much guarantee I'm going to have something like that on the exam, and I'm trying to get an example version of it for you beforehand. I'm hopeful that I will get it out by the end of the weekend so that you can practice taking the kinds of data you would get and analyzing it. And I'll have some walkthroughs of how to use Excel to do what you need to analyze the data. Yeah, so yes, I could see, I could see this being tied to having some experimental data, and then maybe, so we analyzed the activation energies in this case, but we didn't analyze the activation energies in this case. And so maybe this one would predict a positive activation energy, in which case then, okay, let's do a temperature series. If it gets faster with temperature, then this is right. If it gets slower with increasing temperature, this one would be right. Something sort of like that, maybe. Okay. Let's see, there's some stuff in the chat. Uncover the bottom. Did I uncover the ones you wanted? This is the one they wanted? Okay. All right, why is
I
it
actually
plus
need
EA4 when he has the
bottom one.
Okay, parentheses with negative, good. Same number raised to different powers, math property, add exponents. Yeah, that's exactly right. So the principle that was used here, the mathematics principle that was used here is if you have x to the a times x to the b over x to the c, that becomes x to the a plus b minus c. That's the,
Yeah, I didn't see the parentheses and the negative sign
Okay.
outside. It made sense once I
gotcha.
saw
Oh, I'm just
that.
making sure everybody's keeping up with that, because I know that I have a tendency to just write down the steps, and I don't necessarily always put the intermediate steps in there. So I just want to make sure everybody's keeping up with the steps.
Can you move the top left one down and right?
This one here?
The first step. Yeah,
That-
I can't see that first step. I'm actually confused why it's plus K4.
I'm having a bit of trouble hearing you, so it might be best if you would type in. Why? Why that's K4. So the idea is, what we are doing in this case is the steady state approximation, which means that the rate of production of the intermediate, the N2O2, equals the rate of destruction of it, and there are two destruction steps. One of the destruction steps is this one of the destruction steps is this one. And so they're both listed right here. Does that make sense? Okay. All right. So I think, how do you determine the overall rate? I think we've gone through a couple examples of that. This example certainly included rate determining step and included intermediates. The definition of an intermediate is a species that is part of the mechanism that is not part of the overall reaction, that is produced in early steps of the mechanism and destroyed in later steps of the mechanism. That's to distinguish it from something like a catalyst, which you have present at the beginning and then participates in the mechanism but is not in the overall reaction, and it speeds up the reaction. So in this case, the NO3 is an intermediate because it's produced and then destroyed. The N2O2 is an intermediate because it's produced and then destroyed. And there are no catalysts in this mechanism because the only things you start with are the NO and the O2 in both cases. So we don't have a catalyst in that case. And then how do you determine what the intermediate is in a multi-step reaction? Exactly what I just described there. So I think I've gone through the muddiest points that were listed. I am happy to clarify anything here or go on to other questions if anybody has them. Or how are we doing on time? We started, right, we have plenty of time. Okay. Oh, okay. So very first step, how does it go from plus to X? I'm gonna have to know where we're talking about. Were we on this one? Going from plus to times. So here down to here, what I did was I factored out the N2O2 steady state. And so the first term, if you factor that out, is just the K minus 3. The second term, if you factor it out, is the K4O2. Does that make sense? Okay. Yeah, I'm sorry I shuffled the papers so much. Yep, okay. What else can we talk about? So somebody asked when the next exam is. I don't remember. It's on Piazza. Could look that up. Let me look real quick. Yeah, so available 10/22 is what it says here. So 2 weeks from today is when it's supposed to become available. So next week's material, which is going to be the very beginnings of equilibrium, will be on the next exam. So it's going to be kinetics and a little bit of equilibrium. We will have at least 2 more weeks of equilibrium stuff following the exam. So, the equilibrium stuff that will be asked will be on the basic side for it. Yeah. So I would imagine what we're looking at is essentially 2 weeks of kinetics, 1 week of equilibrium that's going to be covered. So you would imagine there to be about twice as much kinetics as there would be equilibrium stuff. I've already pretty much promised you guys that there's going to be some simulated experiment data analysis stuff that'll go on, and that'll be somehow tied into proposed mechanisms and some activation energy kinds of things. So I don't think that I'm going to do anything really crazy with those. It's not going to be a whole host of lots of different questions about it, because I know that it takes a little bit of time to go through those. So when I get out to you the example spreadsheet so that you can run some sample experiments and some sample analyses of the results of the experiments, you're going to be preparing yourself quite well for what you need to be doing there. The equilibrium stuff, obviously, we're starting next week, and it does, the initial introduction to equilibrium comes directly from kinetics. It's all about this forward rate equals the reverse rate, and then let's figure out what we can do with that to determine how much products we end up with at equilibrium and stuff like that. So, so this stuff will feed very nicely into it. And fortunately, actually, there are some reasons why equilibrium, even though it's built on this kinetics, is easier than the kinetics, because all the stuff with intermediates ends up canceling out just automatically. And so equilibrium becomes much simpler than what you've seen here. Has anybody started looking at the activity yet? Group activity? So I've gotten a couple of questions. They were private questions on Piazza, but it might be worth actually talking about a little of my responses to them. So I'm going to share screen here and go back. We'll go here. So let me come back. Nope, I'm in the wrong place. So I want to talk through a couple of the ideas here on the first sort of questions here. So several of the steps that are involved in this development are essentially guiding you through finding a form of one of the equations we've been dealing with that's going to be particularly convenient for this, this particular activity. So just as an example, let's look at this first question that we have. And the reason we're looking at this first question this way is that when we developed all the first order kinetics equations, we did it using rate constants, but what you're given in this problem is not rate constants, you're given half-lives. And so being able to look at the equation in a way that includes half-lives is a very useful thing to do. So let's take a look here. So we know that radioactive decay is a first order process. So the first thing we should do is write down the first order integrated rate law. We are told as well that what we're looking at are parent ions, which we label P, and daughter ions, which we, or not ions, isotopes, which we are label D. And so to be consistent with how geochemists use this notation, we replace the A's with P's for the parent ions. And what we want to do as well is to find an expression where instead of using the K, we are using the half-life. And so remember, for a first order reaction, we found that the half-life equals the natural log of 2 over the rate constant, which means that we can solve this for K to be natural log of 2 over T1/2. That means this can get plugged in here, or there actually. And so we have an alternate expression here that is mathematically equivalent, minus natural log of 2 times T over T1/2, where all of this is in the exponent. And so because you're dealing with half-lives and half-lives it's more convenient to use this expression than it is to use the one with the rate constant in it. Then, you know, the next couple of questions are saying, okay, let's now get the parent and the daughter. Let's get the daughter isotope in here as well. And one thing we know is that every parent turns into a daughter, so we know that however much parent we start with, the current amount of parent plus the current amount of daughter state will be that sum. So you could solve this for P and plug in over here and get this in terms of the daughter isotope. So things like that. So there are several sort of derivation steps that I walk you through like that to get the equation into a form where you can then more easily just plug in the numbers to answer the conceptual questions that are coming up. Okay, so that's the way to think about these. So there's a clarification here. Yes, I misspoke when I said the parent was ions. What I meant was a parent isotope and a daughter isotope. Anything else anybody's interested in? Or terrified of? Will I tell you if a problem is elementary or multiple step, or is there a way to tell by looking at it? Okay, so there are a couple of different ways to answer that. In many cases, yes, I would tell you which it is. If you look at a reaction and you find that the experimental rate law does not match the reaction stoichiometry, then you know it cannot be an elementary step, it must be a multi-step process. So that would be one way you could figure it out, but you would have to have data that would let you determine the rate law in order to do that. You cannot prove that a step is an elementary step just from the kinetics. You can prove it's not by proving that the rate law doesn't match the stoichiometry. But there are plenty of cases where there are mechanisms that are multi-step that produce a rate law that is identical to what you would expect if it were a single step. Now, on the other hand, if you are given a proposed mechanism, that proposed mechanism is assuming that each step along the way is an elementary step. So, in that proposed mechanism, you are intending to lay out each elementary step along the entire pathway. That's about as far as we can go in proving in this. Question, is there a way to change where the quiz bubbles pop up? When they block the screen, it's pretty much impossible to look at the reaction equations to translate into the rate law equations. I have looked for a way to place it somewhere different, and I have not been able to find one. So one thing I have done, though, is I've enabled the ability to click on the rewatch the last segment portion of the video, which should take you back and be able to go see the stuff and pause it and write down what you need before you go through. Now, one thing I have not checked is that once you have watched a section and then click on go back and rewatch the previous section, I would hope that it is set up so that you could then scrub forward to just before the quiz and then pause it there without that counting as not having watched it, so you don't get the so you don't end up with the problems with the quiz scoring. I have not had a chance to test that. Has anybody that's either here or in the chat tried doing it that way to see if it works? I think that as long as you have watched it once during that session, then that will count as having watched that section. So if somebody does ever try that and it either works or doesn't, please let me know so that I can share with people whether that's an okay thing to do. So for the moment, my suggestion is click on rewatch the last section and then pause it so you can see what you need for the quiz. Another thing you could do is have the YouTube version up in the other window and scrub that to wherever, in another window and scrub to where you need to in that one, because it's not monitoring that one at all. So that's another possibility. I wish I had a way to make the quizzes not show, maybe you could minimize the quiz or something. I haven't found a way to do that in the software I'm using yet. All right, well, if there are no other questions, I don't think it's worthwhile for us to just sit here and stare at each other. One thing I could do, if you guys would like, I went through some example mechanisms right here and analyzed them. I could give you guys one to work through and let you work on it, and then we'll check the answers as we go. Would you like to do something like that?
Yes.
Yes, okay. All right, here we go. Let me find something I can write on. Run out of paper. Okay. So we are going to look at the O2, no, we're going to look at decomposition of ozone. 2 ozone molecules, which that's an O3, goes to 3 O2 molecules. And we have O3 goes to O2 plus an oxygen atom. We'll call this rate K1. Step 2 is going to be an oxygen atom plus an O2 goes to O3. So this is the reverse of the previous one. We'll call that K-1. And our step 3 is going to be O plus O3 goes to 2 O2. And we'll call this K2. So since this is reversible right here, let's use the pre-equilibrium approximation for this. You have an and we'll say that this is rate determining. We will say that this is a fast equilibrium. We want to know what is the overall rate law. I'm also going to give you activation energies for each of these steps. And what we would like to know is the overall activation energy. So 103, 0, 21, and these are all in kilojoules per mole. Okay, so. How many people need some more time? Okay. I'm not seeing any hands, so let's take a quick look. So the place to start is with the rate determining step. So we get that from the K2 reaction here. We are using the fast equilibrium. So the forward reaction rate has to equal the reverse reaction rate. So that's what we have here. We identify the O atom as the intermediate species that we need to get rid of in the overall rate. So we solve for that here. We plug that into the overall rate to get this, to discover that this mechanism is second order in ozone and -1 order in O2. And based on the rate constants that we have here, our activation energy is going to be the first one, activation energy for step 1 plus the activation energy for step 2 minus the activation energy for step -1. And so that gives us an overall activation energy of 124 kilojoules per mole. Okay. So say that again, as in the activation energy part. So the idea is that we have e to the minus activation energy over RT in each of these cases. So we add the activation energies for step 1 and step 2, and we subtract the activation energy for step -1 to get a total activation energy of 124 kilojoules per mole, because we have 103 plus 21 minus 0. Oops, switch it off screen. I'm pointing off screen, sorry. Okay. Okay. Are there any questions about this solution?
Were EA to the, for EA -1, where that's 0, wouldn't that
Yes.
just turn your whole bottom into 1? Your whole denominator? Because it's e to the 0, it would be 1.
So with EA -1 being 0, e to the 0 is 1. So what this is saying is that there is no temperature dependence for this reverse reaction.
Okay.
And so finding the question from the chat, so finding the activation energy is simple as adding and subtracting them after you find the rate law. When they are combined by just multiplication and division, yes, that is correct. If you have a case like, where was it? Like this one, where these two are multiplied together, but then you've got 2 that may be added together in the denominator, there it's nowhere near as simple. And so you can't actually combine them in this way unless you do something like we did here to assume that one of the 2 terms goes away. But in terms of when it's added, when they're multiplied or divided, this equation holds. And so, yes, multiplying and dividing rate coefficients means adding and subtracting activation energies. And just as kind of an interesting side note, it is not uncommon at all for a reaction that is a bare atom coming up and attaching to another atom or a molecule to have an activation energy of 0. That is in fact so common that we generally just assume that that's the case because there's no barrier to that forming. The only problem is finding some way to carry off the excess kinetic energy. Okay, well, we've done some good work today, I think. Let's call it quits. Thank you all very much.